Well, thank you all for being here, and thank you, Tana, and the organizers and my colleagues that convinced me to come and give this really daunting title. I did not pick this title, and I just want to say that it's an evolving state. So I'm going to give you my perspective of where we are now and how we got here. I asked many colleagues to send me data where, if they had anything particular to share. And so I have a bit of data to show later in the talk, but mostly I'm going to give you more of a timeline and where I think we are in terms of achievements and gaps at this point. Basically, I think we're at the top of this curve right now. We are starting to move into exponential growth phase for blue carbon science, and it's just really exciting. So we're standing on the shoulders of giants. People have been working on carbon cycling in salt marshes for last 100 years, and it's mostly been outward looking. So basically, what's going on in the marshes in terms of how it affects the ocean, carbon export for trophic support of fisheries, for example, or nitrogen management for preventing eutrophication in estuaries, but always outward looking, not so much inward. And then basically we started looking a little bit more at marshes when people started to get interested in sea level rise and what it might be happening in these environments. So again, blue carbon as a science wasn't happening so much, but maybe carbon cycling and what you might expect to see in, for example, restoring marshes or degraded marshes, how it was changing the soil properties and things like that. I want to give credit to the Chimura et al. Paper in 2003 for comparing salt marshes with terrestrial systems to really make the point that these systems are different, they are huge carbon sinks, and they're not being credited. At the same time, Carlos Stewart and colleagues put out a paper saying that marshes were important in the ocean carbon budget side of things. And it was really these two papers in the early 2000s that set the tone that we really have to focus on the carbon sequestration services of these systems rather than just on their role in the larger ecosystem, or we need to focus on that one type of ecosystem service because we haven't been doing that. And since then, really, blue carbon has taken off. This is a graphic that Ariana Sutton-Greer put together for this a project that I'll talk about in a bit. But at this point, there's papers coming out in Nature and Science pretty much once every 3 months or so, something major about coastal carbon cycling, and there's some component of it that focuses on the carbon storage and fluxes in salt marshes. So we're all over the press right now. We're coming out constantly. The new paper on fjords is causing a little bit of a stir, but the idea that they're storing 11% of the carbon in ocean systems is in these little tiny fjord systems. The other thing picking up too is green infrastructure, and so right now we're seeing links between blue carbon and green infrastructure. Again, what's driving that is this interest in sea level rise, and then also I'm going to call them our frenemies, Sandy and Katrina. They're obviously no human disaster is a good thing, but they certainly shine a light on these important services, and so they're sort of friends of the blue carbon community. And I just think we can go up from here. So I'm expecting the rate of papers coming out in high-profile journals to just keep rising because there's just so much coming out right now. And particularly this group, it's very exciting for me to be here because to me, this is like a coming out party for this incredible project, ecosystem-level accounting that's very rarely done, and I'm hoping we see more of this. So this is really sort of my theme. I think the eyes of the world are on us right now. David Yoskowitz's presentation before me really emphasized that again with the different federal policies that we have. It's international at this point, whether it's regulatory potential or markets or just agency goals. We're just seeing a lot of people interested. And I also want to give credit to basically papers such as the Pendleton paper, the McLeod paper that put these numbers into perspective that could communicate to our grandmothers how important these systems are and so how losing them, for example, leads to big emissions, or if you just look at the rates of carbon burial in these systems, how high they are. It's not just policy that's got our eyes on us right now, it's actually the entire science community that's working on, on carbon accounting. And just from a terrestrial perspective, I'm just going to highlight this one paper. It was, I guess I can't point, but regardless, I'm sure I'm doing this wrong, but regardless, this paper is just a summary of where the carbon budget is now and how it's moving between when we have fossil fuel emissions, how much goes into the atmosphere versus, for example, into the ocean or into the terrestrial ecosystems. And in the past, we always had this balance basically from logging and land use change. We had some inputs, some from fossil fuels, and then the amount that goes into the terrestrial ecosystems was really variable, really high uncertainty, so like 50 to 70% uncertainty in that number. It turns out that when we start to look a little closer where that carbon is in those terrestrial systems, it's not all staying in those terrestrial systems. We give land credit for storing carbon, but about 35% of that is showing up in coastal waters, in freshwater systems, and estuaries. And because that carbon is there, again, these accounting techniques, people are looking to see, is it there, where is it, how is it moving through those systems? So I think we have the eyes of the science world on us right now, big time, just to close these budgets. Again, that's the 35% there, moving into freshwaters, estuaries, and coastal seas. The marine carbon budget has noticed this for a while, but it was summarized well in some recent accounting by Dunn, but basically showing that, of course, yes, we have high productivity in coastal oceans, but in particular, we have really high, we have 86% of the total ocean flux going into coastal sediments, and this includes continental shelf. Of that, basically about 0.7 petagrams of carbon going into that system. About 1.1 to 0.2 is in coastal vegetated systems. So we're potentially about a quarter of what's being stored in these coastal coastal systems. And so, again, this is not meaningless in the terms of the total carbon flux of the ocean. It's actually an important term. It is a pretty small term, though, if you just look at the global flux. So we're really not going to win on numbers. It's a very, very small pool of the total amount of carbon cycling in the world. And it's only, if you just look here at this, this is a diagram of the range of emissions versus uptakes onto the land. Oops. Into the land in green, and then uptake into the ocean in blue, and then what's left over gets into the atmosphere. Basically, we can see the land is really, really variable in terms of its uptake, but it's not impossible for a land surface change to impact the overall budget, because the Indonesian peat fires, for example, in 1997 show up in this signal. So it's true that small changes can make a difference, but I just want to point out we are pretty small compared to the overall fluxes. So what I think our challenges are, before I kind of go into some of the achievements and gaps, is really to do the best science possible. And I think this project that we're going to be focusing on this week is an example of really the best science possible at this point to try to nail some of these questions down. I also want to caution that we don't oversell, because we really don't need to. We have this incredible system, and I'll describe that a little bit later. But we need some real clear terminology on what we mean by saying carbon accumulation versus burial versus storage versus sequestration. Those words get used a lot of times very fluidly, and they're really not the same things. And I'm not even going to fight for one particular direction, but this is an important distinction we need to make, I think. And then finally, and this has been brought up again by David earlier, this is just one ecosystem service among many. And again, I don't think we're going to win on carbon, but we can really win on all of the co-benefits that come along. Wetlands don't necessarily get restored for carbon. They get restored for other benefits, and then this is just a co-benefit we need to capitalize on. So let me just give you an example of why wetlands are great. When you look at different land management techniques for removing carbon from the atmosphere, a lot of times agricultural soils management comes up as a potential way to do this. And it's great, there's a lot of agricultural soils, it works pretty well. But overall, the rates of sequestration are lower, they're orders of magnitude lower in some cases in terms of the rate going into the soil. And it saturates. After a point in time, it doesn't take up any more carbon. So that's something very different than our systems. Our systems do not saturate. And so when you put this in the perspective of other systems, we have a very small footprint, very small area needing attention, and we have high rates of uptake and no saturation. So it can continue through time if the marsh persists, if it's a properly designed and or protected resilient marsh. So let me move into the science a little bit here. There's quite a few efforts that have come up recently. I know that there'll be some posters here, for example, on the wet carb project. And there's also CCARS, which is the coastal carbon synthesis efforts. And these works really are trying to link together all this carbon cycling going on between, as it's coming and going and changing phases and so on, between tidal wetlands, estuaries, and the continental shelf and open ocean. There's a lot of action going on in there. And for that reason, you can't really rely so much on measurements. You have to do a lot of modeling, a lot of remote sensing. So it's a little bit different than what we do in the burial side of things, for example, in salt marshes, where it's more cumulative and directional, and we can actually measure something in the soil and say something about carbon sequestration. This is not a new surprise, or it's not new to this group. I saw there was a lot of scientists in this group, so this is not new, that carbon accumulates as marshes grow. This is very different than a forest. A forest grows because the trees grow. A carbon stock grows there because the trees are growing. The soil eventually will saturate. These systems, the soils don't saturate. They just keep growing. This has been known for a long time. But what controls whether they move, whether they grow out into the water, up into the in elevation, or inland, is really different properties. Progradation out into the ocean is sediment limited, so if you don't have sediment, you cannot possibly grow in that direction. Elevation can be gained both with sediment and organic matter, and that sediment could be organic from the land or inorganic. And physically limited, or physical limitations is really what controls whether sea level rise will allow transgression to happen. If there's a road there, marsh isn't going to move in. If there's a mountain there, marsh isn't going to move in. So these are the growth directions that are important. I do want to point out, though, that it's not, this carbon is always growing because it's being stored under anoxic conditions. Therefore, it's really vulnerable. It's only protected because of the conditions that persist. And therefore, if it's the carbon is very easily lost or drained, lost when the system is eroded, for example, and enters into the open ocean, or is drained, for example, for agricultural land. So those are things we've known for a long time, 50 years at least, but where we're really needing to go now, I think, is in terms of doing the best science possible, is focusing on these data gaps, these general areas, and they're necessary for us to focus on, not just for carbon cycle science, but also for accounting that could be used for markets, for example. And so I just want to go really quickly through 8 examples of areas where we've had achievements, and there's also some gaps and some potential approaches for those in the future. And a lot of these things are going to be touched on because this project already touched on them. There's going to be posters, and there's also some other projects, some posters that have other projects that deal with this as well. So this is just a real, like a teaser of the kind of things that, that we could be focusing on. Data mining. There is so much data out there that we could actually start to put together some general patterns. This is a project I'm one of 18 PIs on. It's a carbon monitoring system project that got funded by NASA just recently, and we're just starting it. The idea is we're not collecting any data, really. We're just using all the data out there to try to come up with an accounting method that could be used for, at a national scale for greenhouse gas inventories. And the project is really distributed across the US using NOAA sea level rise gauges, using SERGO, the USDA soil databases, and using the NOAA CCAP, or Coastal Change Analysis Program, data on changes over time. So again, in 1996 was a system, a wetland or an agricultural field, and then coming back 2010, what is it now? And what that stock change might what kind of stock change might have occurred over that time period. This is just a graphic that the new postdoc we just hired, James Holmquist, put together, and it just shows the 6 sentinel sites where we're really focusing in and basically throwing all our guns at answering this question. And so we're looking not just at soil carbon, but that's one of the focal pools, of course. And the white dots are really the sites of validation. These are where we have cores, where we actually know rates of soil accretion. And so we can validate the model in the end based on over 500 cores that exist across the US. Some other data coming out from that data mining approach is carbon density. Just looking at, here's one of these important variables. If we know how much a marsh is growing, we need to know what the carbon density of that soil is in order to calculate how much carbon is being stored. It turns out there's not as much variability in that pool as we thought. We thought it was going to be really broad, but this meta-analysis from Jim Morris just shows that the average is about 0.03, and what's really interesting is when it's much higher than that. I'm interested in what are the conditions that make it higher than 0.03. That's sort of the global mean, if you will. And it looks like really if you step away from the curve, if you start pushing to the right side of this black curve that has loss on ignition and bulk density on the side of it, 2 very common measures, that's when you start to get these high carbon density concentrations, and that's a question I think we need to ask. All right, another science achievement is these maps that just came out from the Council on Environmental Cooperation, CEC. This is work done by Gail Chimura, Fred Short, and a slew of other people to basically take all the data we had available and figure out in North America where are our seagrasses, where are our mangroves, and where are our salt marshes. And in particular, what are, within those areas too, what are threats, what are some rates? They tried to pull as much data together they could for blue carbon habitat mapping. And I just want to point out a couple of things. One is that there's actually in North America more mangroves than there are salt marshes, which just shocked me. And I think salt marshes is dominating. But the other thing was seagrasses are really, really poorly mapped. And so that's really the direction I think that people want to go now, is try to get a handle on that pool, because again, it's an undermapped resource, and if you don't know where it is, you can't possibly manage it. Then there's a question about subhabitat. So we know just those 3 main categories: seagrass, mangrove, marsh. What about subhabitats? Do they matter for carbon mapping? Does it matter what kind of vegetation you have, what elevation, what particular landform, lagoonal or spit or things like that? And so when we look at other data sources that are available, there's obviously the National Wetlands Inventory. It just came out with the national high quality product last year. It's really the best data set we have of wetlands currently in the US. That's in the upper left corner. The NOAA CCAP data is available across the US. It's been available since 1992. The problem pretty much with CCAP is accuracy, and in particular the difference between palustrin, which means freshwater tidal according to the map, and estuarine habitats, and which is supposed to be more like a salt marsh. It's a little bit blurry, that boundary, so we're going to have to use a lot more of the palustrin areas to get a better handle on actual salt marsh or tidal marsh habitat. I want to just also plug this work being done by Esri with all their ArcInfo engines going on down in Redlands, California. They're working with Roger Sayer at USGS to map the entire world's coasts just based on purely vector recognition of whether there's what's it called, a channel morphology on the coast. And so that map is being generated like right now with all the resources that Esri can put towards it. And then finally, I just want to point out that with LiDAR, we have the ability to look at gradients as opposed to just classes of wetlands, and that changes things, because we've always talked about classes of wetlands, but with gradients, we might be able to say something more about patterns. For stock measurements, this is really one of the untapped things. We do not have good data on stock measurements, and it's because it's really hard to get. We have the top meter of soil, really good, no problem, top meter of soil. You want to get down below that, really difficult, and it's variable within marshes. So for example, this is data on the top from Gail Chmura, just showing that, for example, I believe there might be a poster here on Wells, the marsh there, but you can see that there's some really deep peats within that marsh, and there's some really shallow peats. So it's unevenly distributed. So again, 4 meters deep peat and 1 meter deep peat is within the same area. This picture on the bottom just shows how difficult it is to get these cores down deep. This is work being done in San Francisco Bay. Literally last week they were collecting these cores, and they did some in December as well. A lot of people want to use ground penetrating radar to get depth. Not so good in saline and variably inundated sites. So GPR is a little bit tough to work with in salt marshes. Provenance, I'll just briefly say that provenance, where the carbon came from, some people do not care, some people really care. And getting at the identity of it, the age of it, and the source of it is interesting, perhaps in a terrestrial budget way, but I think it's important overall in looking at fate, because some of it will degrade very quickly and some of it will not. I just want to point out that isotope work to identify whether the source was, for example, a marine-based source or a land-based source. There's multiple isotopes, and I believe Megan will talk about that later. It's getting really cheap, so it's not something that you should avoid doing. You can actually get a good handle on where your carbon came from if you just try to track where it came from. I'm sorry, if you try to track its isotopes. I will just say that the freshwater tidal deltas of California, most of the carbon in the soils is autochthonous. It's produced in place, and you can still see fragments of it. It looks literally still like pieces of roots that was originally there, but it's so vulnerable. I mean, you just add a little bit of oxygen, and this stuff blows off very, very quickly. So it's protected only, not because it's in any way, it's not mineral bound. It's not bound to clays. It's very fluffy, easy to blow off. Resilience and fate. I actually think that resilience is the key to blue carbon accounting. If we don't know if these marshes are going to be around, we can't actually do a lot of this accounting into the future. So this is just Louisiana versus California. They're both basically sediment-starved systems at this point due to human activities. And what's interesting is in Louisiana, there's massive projected loss of salt marshes, and they're already seeing it. And of course, it's often associated with the lack of sediment to fill in the elevation that's caused by the high relative sea level rise. In California, we don't really have that much loss right now. It's projected. But this paper, I just want to point out, just came out in the San Francisco, our local online journal by Kathleen Swanson. And basically, most of her scenarios showed that the marshes were resilient, even in the lack of sediment in the freshwater parts of the delta, which is just fascinating. Again, they have been organic most of their lives, the last 8,000 years, but to show that into the future they might be okay is a pleasant change. What actually happens to carbon in systems is really the question that is most people's concern. If we erode these or submerge them, are we going to lose that carbon? And I just want to point out again that this paper by Pat McGonigal and Matt Kerwin from about 2 years ago is a really good illustration of the fact that with sea level rise, you don't necessarily get immediate loss. The marshes can keep accreting, but they'll hit some tipping point, and every marsh has its own tipping point, and that's what the modeling is trying to figure out is, will a marsh make it or not based on its current conditions and its mineral supply. This is a paper that, I've looked at this for years, and I finally saw, why this is so important. The submerging peats of Louisiana, some of them are staying in place and some of them are eroding away. And this paper was one of the first that really showed paired marshes where this peat core, you can see this sort of shallow 1 meter deep peat, as it got submerged, most of it doesn't degrade within 10 years, but there is some erosion off the top, and you can see that that's the loss, that's the pool that's being lost to the ocean. So we can actually start calculating, I think, some of the erosion rates. Thanks. Oxidation rate is actually modelable as well. It's monitorable if you use elevation as a proxy for oxidation. And this is, again, the Sacramento Delta of California, where I do most of my work. This is a data set from Judy Drexler, a really large group of work and product. And the real point here is we're losing, where they have drained the soils for agriculture, again, with the gold rush bringing food to the miners, they needed to turn this wetland into a agricultural field. We're losing 4 meters, we've lost 4 meters of peat in some of these sites, and if the green represents the remnant wetlands that have not degraded. They're just sitting there doing just fine with sea level rise, but the other systems have subsided through oxidation. Again, very lost. Another site we're losing peat really rapidly is Florida. This is some data from Tiffany Troxler in Louisiana, and she's trying to figure out whether it's sea level rise itself or salinity intrusion. Salinity intrusion, of course, being somewhat controllable because it's being caused by freshwater diversions in the state. Again, a really good experiment. You can just see these tufts of plants still sticking up above the peat. Everything below that has eroded away, and I want to say oxidized away, chemically released. Process-based modeling is another step forward. I won't go into it. I will just point out that we do finally are starting to have some greenhouse gas data that will be useful in modeling from continuous flux. I know there's going to be an eddy flux poster here, and I also know that the gas flux data from here is going to be instrumental. This is data from California, and I just want to point out that we have this. There's a huge tidal signal in here, really hard to pull apart. We're working on that right now, and glad to learn whatever I can from this meeting in terms of telling that story. Nitrous oxide, some sites are uptake, some sites are emission. It really depends on your site, and it depends on what your nitrogen load is. I think here there might be a really good story coming out of Serena's work, and so I'm waiting to see again where this is taking us. I'm just going to close by saying that this sort of ecosystem level blue carbon accounting is the direction I think we should be going, because with these sentinel sites and all of this effort in these particular places, we can start to piece together the pictures of the puzzle and tell why sites are sinks or why sites are sources. I will point out that in Nisqually, where we have a project that's just starting up here, the focus is really on the salmon. So we are trying to link back to ecosystem services that aren't carbon related, but show how the carbon cycling is related to this other ecosystem service of production of these fish. So again, I think this team that we're going to be hearing from for the rest of the day is doing the best science possible. I think they're avoiding overselling really well because they don't have to. It's a really good story to tell, and they're also considering carbon sequestration just one of many of the processes or of the benefits of salt marshes here. And I guess I'll just close by saying I think we're at a great moment. I don't think we should be shying away from the eyes of the world. I think we should absolutely seize this moment and make sure we keep pushing forward on the importance of salt marshes for carbon sequestration, and not just marshes, mangroves and seagrass too. Yeah, thank you.
This is Sally Sims. I'm a conservation consultant. I have a question on that last slide when you talked about ecosystem level blue carbon accounting. What kind of a size geography are you talking about when you are talking about that kind of accounting?
Yeah, I think it's variable. It depends on your site, but almost sort of like a watershed type thing where you can constrain all the players. If you're looking at carbon moving through your system, you can constrain what the terrestrial inputs are and what the marine boundary inputs are. So, you know, scales
watershed
of
level.
Yeah, it was the scale of large marshes. Yeah, so multiple like maybe 100 hectares or something like that. That's the best large scale.
Okay, thank you.
Excellent presentation. I'm missing the biology, the health. Does NOAA or USGS or anybody in this country doing any research on the microbiome of those marshes and those mangroves? We need to have that data.
You mean like the bacterial communities?
Bacteria, yes ma'am, before it goes away. That's the most important thing. That's what the foreign nations are doing now.
Yeah, there's actually a lot of people collecting soils in these marshes and looking at the DNA and the metagenome. You know, what are all the players there? I mean, it's mostly done though, really from a prediction perspective to try to figure out. You know, if I look at the genome, can I know if it's sequestering carbon or producing methane or, you know, have high sulfate reduction and so it's blowing off carbon? You know, all those are the kind of questions people are asking. But there's a lot of data because genome work has gotten to be inexpensive, and it's easy to collect samples and take a look at what's in there. But in terms of what's it called, storing it and like actually, for really studying the communities from a genetic preservation perspective, like, what do we need to know what's there? I don't think that's really the focus. It's always been on who's there and why and what they're doing for a different service, let's say, like metabolically, what are they doing? That's usually the focus. But it's a good question. I should ask folks that I know that are doing it and whether they're preserving any of the strains, yeah.
Thanks, Lisa. That was really nice talk, and I'm pumped now for more of this work. I'm curious, in the Sacramento area, the drained wetlands there, how long have those been drained? And of the ones that are still drained, are they still respiring at a substantial rate?
Yeah, I wanted to talk about that a little more. So the Sacramento wetlands, when I talk about 4 meters of loss, for example, or 6 meters of loss, that happened over 125 years, or maybe less. Very, very, very short time. So these are some of the highest rates of conversion losses like ever recorded on the planet. They're just huge. But what's cool in some respects is that as they respire, you get this kind of black layer. I don't know if you can kind of see this on top of those drained wetlands that builds up, and it's a little bit more mineral. And it impedes the rate of carbon loss because now the surface is not all that fresh material. It's actually sort of the old stuff is at the top. And so the actual rate of decay, the actual rate decays over time, and so you get less and less emissions over time. But the initial rates are real high. But anyway, there's actually models that they just use elevation to do this calculation, and it's always a curve that looks like this. So I don't know if that answered your question. Yeah.
Hi, my name is Rebecca Roth. I'm with the National Estuarine Research Reserve Association. Thank you for your talk. I had a question. You mentioned that the identity, age, and source of carbon is known sporadically in certain locations, and it depends on what people want to know. And I'm curious if you could opine, or you had any intuitive sense on how important that is for a community that's looking at wetland restoration or any type of policy work, if knowing that data has had any influence, or if you've, maybe that's the next social science question, but any thoughts you have on that, I'd be interested to hear.
Well, I think there are at least two groups people could talk to that. Megan and then the Steve Crooks probably, or Steve Emmett Maddox, about why you would want to know or need to know. But the key is that if the carbon in your wetland came from outside the boundary of your wetland, the question is, should you get credit for it? If there's a piece of a tree in your wetland, did your wetland store that carbon, or did the tree store the carbon that now ended up in your wetland? And my opinion is that the wetland should get credit because it provides the environment, it intercepts the carbon before it enters the ocean and then blows off. But this is open science right now about how do you calculate the relative value of that storage, or whether the wetland really provided that carbon storage. But that's really the question that's at the crux of what some people want to know and some people don't want to know. And I think VCS protocol maybe I don't know where it is right now in terms of making that decision, but that is the question of the day, is really, do you need to know if the carbon came from outside of your site? Does that answer your question? Or you probably had
Well, it's probably one of those multi-question questions, so that's helpful in the context.
Yeah.
When we get to that next phase of talking to the grandmas and the public communication of what's going on, some people are more aware. And so I'm just kind of more provocative to me of how you would communicate the, and identify it and the age and the source, not just from the monetary, the market piece of it, but from the do something with it, because it's only one, knowing it is only, you still have to come up with a solution.
Yeah, well, so the thing is, if you know where it came from, then you know the processes that are driving your carbon accretion. So if this storage service is important to you, then you kind of want to know how it works. How is the carbon I'm storing coming from somewhere else, or is it generated on place? And so it's really a matter of how much you want to know whether the carbon sequestration service is contained within here, or whether you're serving a larger role within the wetland. I think it's a question of really of scale and your interest in your marsh. And I guess my other thought is that we need more data, and it's inexpensive, and so if you're collecting the samples anyway, I feel like we should start to be piecing together a story, because maybe all the East Coast marshes are storing trees and all the West Coast marshes are not, or I have no idea. I'm just throwing out that there's potential regional differences we might be able to pull out of these surveys.
Very nice talk, and thank you. Particularly, I want to thank you for pointing out the confusion of the terminology used in this field. I think in the terrestrial carbon cycle point of view, people are kind of merging and people understand each other well. But in the wetland, carbon science and blue carbon science is newer, and also people involved scientists from the terrestrial ecologists and the oceanography and wetland science, they're all involved in this field. The people use different terminology in identify the carbon stock, carbon flux. So what do you think is the best way to use some kind of terminology to convey the information to the end user or to public? Because now we know in the scientific field that we are confused by ourselves, but how can we solve this issue to deliver a clear message to the general public?
I think that's a great discussion for the rest of the day. I'll tell you what my thoughts are on it real quick. I think timescales is what's important. So I think if you're going to use any one of those words, you should have some sort of timescale associated with it, or put some barrier on it. And that's what we do right now with the IPCC estimates of, for example, methane or CO2 equivalents. We talk about residence time in the atmosphere. So when we say methane is 25 times more effective than CO2 in terms of its climate effects, that's within a 100-year window. If you want to change it to a shorter window or a longer window, it's a different number. But we all agree that we're going to talk about the 100-year time frame, and we're going to use the number 25 or something like that. So I feel like if we can get to some number where we say we can put a time scale associated with it, so maybe a 100-year sequestration rate or something along those lines, then we would at least be able to be talking apples and apples, and that's where I think is missing right now. Because 1 year accumulation can be, again, just to put this in perspective, you could have 1 year accumulation that's really high, 300 grams of carbon stored, wow, but the truth is 200 of it's going to blow off within the next 2 years, and your real long-term rate is 100. But if you report 300, then everybody gets all excited, but the truth is, it's not going to be there. It's going to be this lower rate. And so what do we want to report? The short-term rate or the long-term rate? And that's why I feel like a number might help. And because there's reasons to report the shorter rate. There's reasons to report the 300 because people trying to close continental scale budgets, they want that number. So I'm not saying that one's better than the other, just be clear. But Jim, I think that's a great question. I'd love to ask you more too, what you think.